The limit of sequence, we define it to be limit as n goes to infinity, an equals a real number L. It's important to know that this is a limit behavior. We only care about the tail of the sequence. So we'll draw a picture. This is the an and n axis. Okay, so n can begin with 1, 2, 3, 4, 5, 6, 7, and so on. And A1 can be up here, A2 can be down here, A3 can be up here, A4 can be up here, and then A5 can be down here. It doesn't matter what happened in the finitely many terms in the beginning. We care about what happened as n goes to infinity, okay? So if we keep having a tail that is converging to a number L, then we call that the sequence converge. Doesn't matter the relationship of A1 to L. So this is important to know, and we'll take a look at example 5.3 to find the limits of a sequence and determine whether a sequence is convergent or not. So for A, we have 5 minus 3 divided by n squared. So in order to find out whether it's convergent or not, we just need to find whether there's a limit. So we take the limits of the nth term formula as n goes to infinity. What's going to happen? Well, limit of a constant, we get constant phi. And limit of 3 over n squared. Okay, so 3 over, you plug in infinity. A number over infinity will give us 0. So this term will go to 0. So we notice that this limit is phi. So because we have limit as n goes to infinity, an equals phi, this sequence, an, converge. So that is our conclusion, and it converges to a limit phi. So that's an easy one. Let's take a look at part B. Part B, so we have a sequence 3n to the 4th power minus 7n squared plus 5 divided by 6 minus 4n to the 4th power. Again, we take the limit as n goes to infinity. And we have seen this kind of limit before in calculus 1. We will divide the top and bottom by the highest power, so n to the 4th power. So it's equivalent to the limit as n goes to infinity. So each term you divide it by n to the 4th power, right? So this term you divide it by n to the 4th power, you get 3. And the second term divided by n to the 4th power, you get negative 7 over n squared plus 5 over n to the 4th power. Okay? So you divide term by term. Similarly, for the bottom is 6 over n to the 4th power minus 4. So then, you know, okay, when you replace n by infinity, this is 0, that is 0, and that is 0. So what you will have left is 3 divided by negative 4. So the limit is negative 3 over 4, and we also call the sequence converge. Part C. So we have this sequence 2 to the nth power divided by n squared. Okay, so we want to find the limit. So we want to find as n goes to infinity, what is the limit for an? So what we need to do in here, we have, so if we plug in limit as n goes to infinity, 2 to the nth power n squared, we get 2 to the infinity power divided by infinity squared. It's infinity over infinity, but sometimes infinity over infinity can turn out to be a constant, 0 or infinity. So there are 3 different possibilities: infinity, a constant, or 0. So we need to use or apply the rules that we have learned, and I'm going to remind you, whenever we have, this is essentially infinity over infinity in determinant form, we will apply the L'Hopital's rule. So I'm going to remind you what the L'Hopital's rule is. So if we're interested in a limit as x goes to a, now a here can be any real number or negative infinity or infinity. So if we have two functions, f of x divided by g of x, and when we have the indeterminate form, which are infinity over infinity plus or minus, okay, or 0 over 0. So if we have these 3 situations, or this however many combination or situation, then what we can do is equivalent to finding x goes to the same constant or infinity, but we just take the derivative. Okay, we take the derivative of the top independently and the bottom independently. That limit will be the same as the limit that we are looking for. So that is basically what the L'Hopital's rule is telling us. It tells us that if we have indeterminate form, we can transform it into the derivative. Now, note that if we have 0 over infinity, you don't need to do anything. It's 0, okay? That is not an indeterminate form. It's a constant over infinity, it goes to 0, okay? So be very careful how to apply the L'Hopital's rule correctly and when to apply it. So now we do have this indeterminate form. So n goes to infinity, 2 to the nth power n squared. You can consider x as n also, okay? They are essentially a function. You replace n by x, you're gonna get the same expression. So we will equal, and we denote we're using L'Hopital's rule, okay? So we'll get limit as n goes to infinity. What happened here, we're going to take the derivative of 2 to the nth power, and we take the derivative of n squared separately, okay? So the derivative of 2 to the nth power is 2 to the nth power times ln of 2. And the limit for n squared is 2n. Okay, then we plug in again. We still see 2 to the nth power goes to infinity, and the bottom 2 times n is still infinity. So we still have infinity over infinity. So what we will do is we apply the L'Hopital's rule again. So we get limit as n goes to infinity. So for the first one, okay, so we're going to take derivative again. Same here. It's easier for the bottom 2n derivative, you just get 2. But for the top, constant, right, ln of 2 times the derivative of 2 to the n, and you multiply by ln of 2 again, so it's ln of 2 squared. Now you plug in again, you get infinity over 2. So we can conclude that our limit goes to infinity. And that should be, if you know which way or which function, the growth of a function, which function grow the fastest. Here's the general rule, okay? A linear function, which is just like c times x, is not going to grow as much as a polynomial, which is like x to the nth power. And it's not going to grow as fast as exponent, which is like 2 to the nth power, e to the nth power. And that is not going to grow as fast as factorial, which is n factorial. So that is something that you can keep in mind. Now, because we have an exponent over a polynomial, we know exponent grow way faster than polynomial. We know that the infinity on the top is bigger. So we will get infinity. So that is a general rule. But if you don't know about this kind of rule, just apply the L'Hopital's rule. So that is part C. Part D. Again, that's why limit is so important in Calculus 1. Now we are taking limit all the time in order to understand convergency and study sequence and series. So in part D, the sequence is of the form 1 plus 4 divided by n to the nth power. Now, if you kind of remember interest rate, it might look like it, okay? So if you remember how we handle interest rate in the previous chapters, you realize this limit, if you call this as y, how do we handle it? Is we have to take ln of y. We don't know how to take limit when there's an infinity in the exponent. So we have to take ln of y to drag. So you take ln on both sides. The exponent here is going to drag down, okay? You're going to get n times ln of 1 plus 4 divided by n. And it's much easier to handle when you don't need to worry about like how do I take a limit with exponent. So in this sense, we use some rule of logarithm. Okay, so now we have this expression that we need to take the limit. So now we take the limit as n goes to infinity, n times ln of 1 plus 4 over n. So if we do a direct substitution, we get infinity times ln of 1 plus 4 divided by infinity, which is infinity times ln of 1 plus 0, which is infinity times ln of 1, right? So ln of 1 goes to 0. So we have infinity times 0. Do we do L'Hopital's rule? No, because it's not infinity over infinity or 0 over 0. We don't have that form. We have infinity times 0. So what we will need to do is we need to transform. Okay, we need transformation. We need a fraction. And usually, how do we do a fraction? Is we handle a term like this and we change it to divided by 1 over n. Divided by 1 over n is the same as multiplied by the reciprocal, which is n. So those are tricks that we usually employ to deal with infinity, limits. So now we do limit as n goes to infinity, ln of 1 plus 4 over n divided by 1 over n. These two expressions is similar, equivalent. But now in this case, we have 1 over n as n goes to infinity, 0. The top, ln of 1 goes to 0. So we have 0 over 0. So we can apply the L'Hopital's rule. So we get limit as n goes to infinity. Now, for the top, we have to take the derivative with respect to x. So ln n. So ln, we have to use a chain rule also, okay? So ln will give us 1 over 1 plus 4 over n. So 1 over the inner function, then times the derivative, 1 plus 4 over n of the inner function. Now the bottom is just power rule, right? N to the negative 1 power, so it's negative n to the negative 2 power. Okay, so now we just simplify the function on the derivative of 1 plus 4 over n. Derivative of 1 plus 4 over n, so 1 plus 4 over n, you take the derivative. A derivative of 1 is 0. Derivative of 4 over n is negative 4 times n to the negative 2 power. Okay, constant. Constant times a power rule, right? So now we get negative 4 times n to the negative 2 power. So we see some cancellation here and there, and here and here. Now we just simplify it. So we have limit n goes to infinity. So now it's basically you're dividing the numerator by 1. So get rid of so just the numerator remains. So 4 over 1 plus 4 over n. Okay. So now we can find out this limit easily. You plug in n goes to infinity. You just get 4 over 1 plus 0, so it's just 4. So that limit is 4, which is telling us limit as n goes to infinity. ln of y equals 4. And what is the limit as n goes to infinity of y? We raise everything to the natural number e, so e to the 4th power. Okay, raise everything to the exponent. So finally, what we have, because we define y, so y is 1 plus 4 over n to to the nth power. So we know that limit as n goes to infinity of this y equals e to the 4th power. In that case, this sequence 1 plus 4 over n raised to the nth power converge.